Chapter 22, Heat Engines and the Second Law of Thermodynamics. We have studied so far the so-called first law of thermodynamics, which is basically conservation of energy. It says that for something to happen, say from initial to a final state, it is necessary that the initial energy be equal to the final energy. That's the conservation of energy. This is a necessary condition for anything to happen. But that doesn't solve all the problem. The question now is this condition also an adequate condition? And that is, if the initial energy is equal to the final energy, is it true then that this process from initial to final definitely is going to happen? Well, the thing is, if E initial equals E final, then of course E final is also equal to E initial, right? So if the conservation of energy is all that is required for something to happen, then since E final equals E initial, then of course this means that the final state can always go back to the initial state. Does that sound right? Well, what that means is that all processes going from initial to final can also go backwards from final to initial. In other words, all processes become reversible. Is that true? Well, our life experience tells us this is certainly not true. As a matter of fact, a lot of things in life can only happen in one direction. In other words, they're not reversible. They're what's called irreversible. Can you give me an example of irreversible process? Well, for example, a chicken can hatch, an egg, that is what I mean, can hatch and become a chicken, right? But can a chicken go back to the state of an egg? You know, that never happens. Okay, so an egg hatching to be a chicken, this is certainly an irreversible process. And there are many different types of irreversible process. For example, when you drive a car, okay, you step on a brake, and the car slows down and loses kinetic energy. Of course, energy is not all really gone. It just becomes the thermal energy in the brake pads and also dissipated into the air. Right? This process can certainly happen, but can this process go backwards? Can it reverse itself? In other words, is it possible for the engine, for the car, for the brake pads to cool off, okay, for the air around the brake to cool off, and for the car to regain the kinetic energy and speed away from stationary? You know, it's a good thing that things like that do not happen backwards, otherwise the world is a very dangerous place, right? So our common sense tells us that a lot of the processes are irreversible. In fact, there are far more irreversible processes than there are reversible ones. And for this reason, if somebody shoots a movie and plays it backwards, you can almost immediately recognize something's wrong, right? Because, you know, obviously the thing is being played backwards because certain things are not possible going backwards. This tells us there is some sort of arrow of time. It's invisible, but it's certainly there. For something to happen, you must follow the correct direction of the arrow of time. For example, an egg hatches, become a chicken. But you reverse that direction of arrow, so a chicken becomes an egg. That doesn't make any sense because it violates the direction of the arrow of time. This is from common sense. But the first law of thermodynamics does not address that issue. Why is there an arrow of time? Because if E initial equals E final, then E final has got to be also got to be equal to E initial, and there is no reason why the actual process can only happen in one way and not the other from the first law point of view. So therefore, we would need something in addition to the first law, which is called the second law, which is why we're studying this chapter. As a matter of fact, if the first law is the only law that governs whether a process is going to happen or not, then we can make certain things happen that's almost too good to be true. Take a look. I am going to propose here a so-called solution to the energy crisis. We know the world is running out of fossil fuel, okay? But are there ways we can get energy from other means without using fossil fuel? Well, if conservation of energy is all there is to it, then what that means is that, you know, if there's a way for me to take energy from somewhere else, then in principle I can convert that energy to whatever I need to use and solve the energy crisis. For example, you know, the world is covered with water, over 70% of its surface, right? There is a lot of water. The water has a temperature, the ocean water has a certain temperature, and of course water is among the substances with the largest value of specific heat. So there's a lot of thermal energy stored in water, in the ocean. How about if I lower the ocean temperature worldwide by only 1/10 of a degree Celsius? That doesn't sound like much, right? It's not going to cause any devastating effect or of any sort if it's only 1/10 of a degree. Now my question is, in doing so, how much energy can you extract from this water, the ocean of the world? Well, you do some research and you find that the volume of the three major oceans, the Pacific, the Atlantic, and Indian Oceans, if you add the volumes together, they're about equal to 1,315 million cubic kilometers. Okay, each kilometer is 1,000 meters and so on. So you do this math, you do this conversion, you find the volume of the ocean, of the three oceans, is about 1.3 times 10 to the 18 meter cubed. And that can give you the mass of the ocean water, of the three oceans. Each cubic meter of water has a mass of about 1,000 kilograms. So that translates to about 1.3 times 10 to the 21 kilograms. All right, that's a lot. Now, if you lower the temperature of this much water by 1/10 of a degree, how much heat can you extract? Well, that's a simple calculation, Cm delta T, right? Here it is, the specific heat of water is 4.2 kilojoules per Celsius degree per kilogram, times the mass, times the temperature change, and here's what you get, 5.5 times 10 to the 23 joules. Okay, now how does that compare with the annual energy consumption of this planet? Well, we are consuming energy in a very, very large quantity. As a matter of fact, the annual production, the current annual production of all fossil fuels, primarily oil, of course, you got coal or whatever, but if worldwide, if you convert everything to the equivalent of oil, it turns out to be about 6.8 times 10 to the 13 kilograms of oil worldwide every year. And each kilogram of oil can release 40 megajoules of energy when you burn it. So that corresponds to the total energy that we extract from fossil fuel every year of 2.7 times 10 to the 21 joules. Now remember, the energy we needed that can be extracted to lower the temperature of the water worldwide by 1/10 of a degree is 5 times 10 to the 23 joules. Okay, now if you divide this by the energy we need from world's fossil fuel every year, you find that the energy that's embedded in 1/10 of a degree of temperature change for the ocean worldwide is good enough to support the world's energy consumption, the fossil fuel consumption for the next 200 years. Now, that of course is quite a good number. If it is realistic to actually extract this energy from the ocean water by lowering its temperature by only 1/10 of a degree, we don't have to worry about the energy crisis for the next 200 years. Wouldn't that be nice? How come nobody's proposing to do that? Well, there is no violation of the conservation of energy, right? You got energy somewhere. It's by lowering the temperature of the ocean water. How come it doesn't work? Well, turns out that the first law is not the only thing that we have to observe. There's something also called the second law. And the second law of thermodynamics, historically, was not set to be discovered directly. Rather, it was discovered from something that is far more practical, and that is, how do you design a very efficient, or the most efficient possible, heat engine? So, let me add some historical note here. Historically, during the European Industrial Revolution, one of the things that people were very interested in is to design a heat engine. And then they want to figure out what kind of heat engine will have the highest possible efficiency. So what's a heat engine? Well, the heat engine operates with a temperature difference. Okay, here's the engine. Here's a diagram of the engine, just a schematic diagram. Here's the engine. What the engine does is that it extracts heat. It absorbs heat from a high temperature source. I use red color for high temperature. TH. H means hot. Okay, you extract energy, extract heat from this high temperature source in the amount of QH. And when you get that energy input part of it is being used to do work. Part of it is being used, is actually dumped to the cold temperature source. T at temperature Tc. C here means cold. Okay, so this is what the engine does once again. It takes energy from a high temperature source, use part of it to do work, and waste another part, just dump it to the low temperature source. If this is an ideal situation where there's no friction, no design flaws, whatever, then we can say that 100% of the heat that you take in is used to do work plus dump to the cold temperature source. QH equals W plus QC. In other words, you don't worry about the engine itself, losing energy due to friction or whatever. So you have this. This really is the first law of thermodynamics, right? At this point, let us define what's called the efficiency of the engine. What's an efficiency? Well, the reason why you want to take some energy out from the high temperature source is because you want to do work, right? Now, ideally, you want to take all this energy that you get from high temperature source, you want to convert 100% to work. In reality, you cannot quite achieve that. So you say maybe for every 10 joules that I extract here, 8 joules is used to do work. Of course, the efficiency will be 80%, right? In general, the efficiency E is defined as the work output W divided by the heat absorbed from the high temperature source. Okay, so ideally we want E to be 100%, which means no heat is wasted on the low temperature source. Every bit of energy that you get from high temperature source is used to do work. That would be ideal. So the question is, can E really be 100%? Okay, that will be really good. However, it turns out there is something called the second law of thermodynamics, which unfortunately prevents us from doing that, from achieving that. The thing about second law of thermodynamics is that there are countless numbers of equivalent statements. Okay, they're all equivalent, which means from one I can prove the other, and so on. What is the second law of thermodynamics? Basically, it is telling you that certain things cannot happen. Okay, certain things cannot happen, and there are many things that cannot happen. And if you can prove one cannot happen, and all the others cannot happen either. Historically, there are two out of these many statements that are particularly famous. So we're going to take these two statements and see what these two statements can lead to. Why do they lead to the fact that E can never be quite 100%? Okay, the first thing is the so-called Clausius Statement. And then you have the so-called Kelvin-Planck Statement. They're equivalent. The Clausius Statement says that no matter what you do, okay, no matter what you do, you have a source at high temperature, another source at low temperature. It says that it is not quite possible for you to pump heat from low temperature to the high temperature source without doing anything else. Okay, in other words, all you did was to pump some heat from low temperature to high temperature source, and nothing else gets done. Just a transfer of heat directly. And the Clausius Statement says this simply is not possible. Well, as a matter of fact, common sense tells us this is not quite possible. It would be too good to be true. For example, can you think of a case where we want to extract heat from a low temperature source and dump it to the high temperature source against nature? I mean, naturally, of course, heat will flow spontaneously from high to low temperature, right? But do we have an opportunity? Sometimes we want to take the heat from low temperature source and dump to the high temperature source. Well, you have something like that in your kitchen. What is that? Yeah, a refrigerator, right? That's what a refrigerator does. It pumps heat from low temperature, which is inside the refrigerator, and dump it to the exterior, which is the kitchen. Okay, now can this happen just by itself? If it happens by itself, then your refrigerator does not need any electricity, does it? You don't have to put in any work. It just does it by itself. Or the air conditioner will also work magically all by itself, right? Heat will be pumped automatically in a hot day from inside your house to outside. You don't have to do anything. You don't have to use electricity at all. And we know this is too good to be true. Our experience tells us that does not happen. Actually, this is exactly an example of the Clausius Statement. You cannot simply extract heat from cold and dump it to the high temperature source without changing anything. You have to do something. For example, you have to plug in a power supply, you have to, use electricity, whatever. Something has to happen. Okay. And a related statement is called Kelvin-Planck statement. The Kelvin-Planck statement has something directly to do with the heat engine. Okay, basically the heat engine, what the heat engine does is that it takes this much heat, Q, right, and from high temperature source, and it uses part of it to do work, and then whatever is left, it dumps it to the low temperature source. Okay, the Kelvin-Planck statement tells you that no matter what you do, part of that heat that you get from a high temperature source must be dumped to the cold temperature source. You cannot simply kill this term and equate these two. Of course, if you were able to do that, then E would be 100%, right? Because W over QH would be 1, because there is no such a term. But the Kelvin-Planck statement prevents that from happening. What it is saying is that no matter what you do, part of the energy that you get from a high temperature source is actually wasted. You cannot convert heat to do work 100% without changing anything else. Okay, so E is definitely less than 100%. That's what the Kelvin-Planck statement says. Okay, I must emphasize on one thing, and that is when I say you cannot convert heat 100% to work, this is a qualified statement. It doesn't mean this will never happen. Okay, it doesn't mean that under no circumstances can we just take heat and convert to work 100%. What it means is that if that happens, then something else must also happen at the same time. I cannot simply convert heat to work without disturbing anything. Let me give you an example to show what I mean. Suppose I have a tank of gas, okay, and here's a piston. Here's a piston. You can connect the piston to a turbine so that you can turn it. You can turn the turbine, you can produce electricity, whatever you do. Okay, and inside this piston we got gas, okay, some sort of ideal gas at a certain volume. Now what I can do is I can heat the gas up. Okay, I can burn coal, whatever. I can heat the gas up. Here's flame going in. Okay, and that's going to raise the temperature, right? Now, that's going to raise the temperature unless I allow the piston to move forward in such a way that the process is isothermal. Right? This can, in theory, can happen. Isothermal process, so that the volume increases, the pressure drops, but the temperature remains the same. So imagine there's an isothermal process. So at the end, after a time, you'll find the piston has moved forward. Right? The piston has moved forward. So the volume increases. Here's initial state. Here's final state. Now, T initial equals T final, because I make the process isothermal. If it's an ideal gas, that means the energy of the initial state for the gas equals the energy of the final state for the gas. Right? Since energy are the same, there is no change in internal energy of the gas. What did that tell you? From the first law of thermodynamics. That tells me that whatever heat I absorb, the gas absorbed from the high temperature source, QH, is used to do work and work only. Normally you say, okay, I have to add, delta E internal, right? According to the first law of thermodynamics, right? But this is not happening here for an isothermal process. Since the temperature does not change for an ideal gas, that means the internal energy doesn't change, which means you don't have that term. Okay, now what did I do? I have taken in some heat and converted to work with 100% efficiency. Okay? W equals QH. Now, does that mean I've just violated the second law of thermodynamics, especially the Kelvin-Planck statement? No, not really. Because you have to understand the Kelvin-Planck statement says you cannot convert Q to W without changing anything else. You look at the initial state and final state. Is it true that nothing has actually changed? Well, can you point to me at least one thing that actually has changed from initial to final? Well, obviously, the volume has increased. Do you see that? The volume of the gas has increased. Now, how do you make sure the volume does not increase, so eventually go back to the same volume, and yet you still maintain Q equal to W? Well, if I can somehow manage to do this, okay, I say, all right, this is not quite the final state. Rather, here's the final state. You got the piston, right? The piston has been pushed forward, right? Now, how about this? How about, for some weird reason, the gas molecules decide to shrink back, okay? They decide to all move that way to occupy less space, all right? So the piston goes back to the original position, so that you go from here to there. The gas automatically shrinks back, and then of course, yeah, the initial final state are identical, right? Now, going from here to there requires that the gas shrink back. Does that violate conservation of energy? No, it doesn't. The gas molecules, all we have to do is have to make sure the gas molecules go that way. Okay, they don't have to do work. They don't have to convert any, absorb any heat or whatever. But have you ever seen this happening? I mean, you have seen gases expanding, right? Into empty space. Have you seen a tank of gas automatically shrink to half its own size without somebody pushing on it? This does not happen, does it? Okay, when the gas expands into vacuum, we call it free expansion. Here, this is not free expansion, it's free shrinking, right? So it is this step to that step that is not quite possible, and that means the Kelvin-Planck statement actually prevents this process from going here to there. Okay, so here, what we found is that a certain event is not quite possible, and that is the shrinking of the gas automatically by itself. That is not possible. And the impossibility of that process guarantees, for this problem, it guarantees the correctness of the Kelvin-Planck statement. So you see, all these, as I said, all these impossibilities are really equivalent, they're linked to one another. If I know that the free shrinking in this case is impossible, then of course it is also, consequently it is not possible to get QH to convert 100% to W without, changing a thing. In other words, the Kelvin-Planck statement holds true. Okay, so this is just an example to show you that all these different statements of the second law are really equivalent to each other. So clearly, the second law, by pointing out an impossibility, it clearly tells you that certain things can only proceed one way but not the other. Okay, it is some sort of criteria for whether a certain process can happen one way or can happen both ways. In other words, are they reversible or irreversible? Okay, so let us take a closer look at two engines. One is a reversible engine, and the other is an irreversible engine, which means that engine can only operate in one direction, cannot run backwards. Let's compare the efficiency between